Right, in this video, we're going to talk about parabolas, how to graph them in particular. And so a parabola, your basic parabola, is going to be a function that has an x squared in it. That's the highest power of x. This is a good time to introduce possibly some new notation. We're going to graph four parabolas on this set of axes. Um, and when we say f of x equals x squared, f of x is a function notation, but it's really just a fancy name for y. So when you see f of x, g of x, h of x, just think of that's the same as y. Y equals x squared, y equals negative x squared. One uh, reason to use this notation is we can now refer to them as different graphs, right? If they all look like y equals x squared, y equals negative x squared, we wouldn't be able to tell the difference. But if we give them different names, you can use different letters, f of x, g of x, h of x, and we can sort of distinguish between the two. But there are other reasons which we will get into. So we're going to graph all these together. So let's put our first parabola, and I'm going to try to color code this, f of x equals x squared. Some of you might know what that looks like. If you don't, one thing we can always do is make a t table and pick some points and evaluate the y value. Remember, this is the same as y. F of x is y. So if I pick some negative values, maybe I go -2, -1, 0, 1, 2, and of course my function is x squared, so the y values would just be squaring these. I'm going to get 4, 1, 0, 1, 4. I'm going to add these to my graph. So I'll start with 0, 0. And we'll call that the origin. So 0, 0 is the right where the x and y axis intersect. I have 1, 1, over 1, up 1 is a point on my graph, 2, 4, 2, 4, -1, 1, -2, +4. If I kept going, if I put 3 in, you would see I get 9 because 3 squared is 9. And if I put -3 in, I'm going to get 9 as well. So my parabola, f of x equals x squared, is going to look like this. And this right here, I'm going to highlight this one. This is what we're going to call the most basic parabola. This is our base graph. Sometimes it gets explained as a parent graph because all the other parabolas can be thought of as just versions of this one. For example, let's do g of x. Let's do this one in red. If I want to graph g of x, which is just the negative of x squared, and I start plugging in the same values, if I take -2, remember at order of operations, you square it first, so that gives you 4, but then I apply the negative. That's going to give me -4. -1 squared is 1, but then I apply the negative, that becomes -1. This will be 0. This will be -1. This will be -4. So if I plot those points, 1, -1, 2, -4, -1, -1, -2, -4, and I could do 3, it would have been -9. -3 would have been also -9. And we can see that we get this parabola. So this is g of x, which was -x squared. Maybe I should label the other one this was f of x, which is +x squared. And we can see what is the difference between those two. By just having this negative, it literally is just the graph of f of x equals +x squared reflected over the x-axis. It's a downward-facing parabola instead of an upward-facing parabola. And so we want to remember that if you put a negative in front of the x squared, it's going to be a downward-facing parabola. Okay, let's do h of x. Let's do that. What do I have here? I've got orange. Let's do that in orange. And we could plot some points again. -x squared plus 9. So -2, -1, 0, 1, 2. You can plug in any x values. I'm just trying to pick some numbers close to the origin. If I plug in -2 squared, I get 4. Then apply the negative. That's -4. And then I add 9 to that. That's going to give me 5. Negative 1 squared is 1. Apply the negative is negative 1 plus 9 is 8. 0 is going to be, this will be 0, add 9. This is going to be 8. This is going to be 5. So this parabola, let me start with 0, 9. 0, 9 up there. I have negative 1, 8 and positive 1, 8. So when x is 1 and negative 1, I'm going to get 8. Starting to notice that the parabolas are symmetrical, right? If I plug in 2, I'm going to get 5. And if I plug in negative 2, I'm going to get 5. And we could keep going here, and what we would see is, I missed a little bit. That's okay. Our parabola here is going to look like this. And so what has happened to this parabola, if you think about it, that looks just like this parabola, negative x squared. The only difference is the high point has moved up 9 units. And so literally what we can think of is this plus 9 is going to be, it's going to be the same as this graph. It's just shifting that graph up 9 units. Some of you know there's this idea of graph transformations. When you see a number hanging out at the end of a function that you already know the graph of, that's just going to lift your graph up or down. By the way, I have talked for a few minutes about parabolas, and I have neglected to mention one of the most important points on a parabola is where the parabola, if it's an upward facing parabola, I'm sorry, a downward facing parabola, where it has its high point, and if it's an upward facing parabola, where it has its low point. That point is referred to as the vertex. So the vertex of a parabola is where it turns around from being going up and then going down, or going down and then going up. So the vertex of our regular base parabola, x squared, would be 0, 0. Same thing for this one. The vertex of this one would be 0, 9. So how about I just draw right here? This would be the vertex, is 0, 9. Okay. So using what we learned on this graph, if I want to graph j of x, I could plot some points, of course, but I could then also just think about it this way, that without that minus 4 there, that graph is the same as f of x, this light blue one. So putting a minus 4 literally is just going to move the whole graph down 4 units. Let's do this one in green. So this is just the graph of f of x equals x squared moved down 4 units. So down here, the vertex is going to be at 0, -4. I could plot some points. I think it will cross the x-axis at 2 and -2. And it's going to look like this. You know, it's hard to see all 4 of those graphs on the same one, but we're trying to do a lot of things at once here without having to have a new graph for each one here. Okay, so what's the takeaway from this one other than knowing the base graph, knowing that when there's a negative, it opens downward? Let's write that down. So f of x equals x squared opens up, opens up. So that's going to look like this. If I have a function that is negative x squared, that's going to open down. So it's going to look like this. If I've got a function where it's, let's say, x squared plus or minus some number at the end, like k, what we learned from the last 2 examples is if you're adding something, it's going to move the graph up by that amount. If you're subtracting something at the end, it's going to move it down. So this right here moves the graph up or down k units. So that's probably, we're going to kind of build to the sort of the general formula for a parabola. Okay, let's move on. Apologize, this video is going to probably be a little longer. There's a lot of stuff to talk about with parabolas. Okay, let's do 4 more parabolas, and I just wanted to get I want to compare it to the base graph. Like I said, this is our base parabola, the most basic one. f of x equals x squared. We graphed that on the last page, so I'm just going to quickly, whoops, that'd be 2, 4. I'm going to quickly generate that one. Okay, so here's our, and since f of x is a fancy name for y, I'm just going to write that as y equals x squared. Let's try g of x. What does it mean to put a number in front of that? 2 times x squared. Well, this is probably a good time to do a table here. Let's see what happens. So if I do -2, -1, 0, 1, 2, squaring -2 is going to give me 4, but then I multiply it by 2, I'm actually going to get 8. This is going to give me -1 squared is 1 times 2 is 2. This will give me 0. This will give me 2. This will give me 8. So it still goes through the origin, 0, 0. But instead of going through 1, 1, it's going to go through 1, 2. Instead of going through 2, 4, which is, let's actually emphasize this. This is 2, 4. This is 1, 1. Instead of going through 2, 4, we go through 2, 8. So notice what's happening is it's actually doubling my y values. From my base parabola, it's just doubling it. But negative numbers are going to be the same. It's going to be -1, +2, -2, +8. So if I put this together, that's going to look like this. This is g of x. So what you can see is it's kind of a steeper version of the base parabola. Your y values are doubled, so it's making it look like a more narrow parabola. Let's compare that to what if I did h of x equals -1/2 x squared. The negative mean tells us it's going to open down. Let's see what the 1/2 does. I'm just going to put y equals -1/2 x squared. -2, -1, 0, 1, 2. If you square that, that's 4 times -1/2 is going to be -2. This will be 1 times -1/2 is -1/2. That'll be 0. This will be 1/2. This will be +2. So 0, 0. Instead of, so I'm comparing to our base graph. Our base graph, when x is 1, y is 1. But in this one, when x is 1, y is, it's actually going to be -1/2, aren't these? Because it's going to be negative. So it's basically halving the y value. So that's 1, -1/2. Same thing with -1. Instead of 2, 4, I'm getting 2, -2. So I'm taking half of that number. And of course, the negative comes from this. So 2, -2 would be there. -2, -2 would be there. And if you continued, what you'd see is you're getting a wider parabola. Okay. So one of the things we learn, we'll do this one, tackle this one at the end, is that we know about the plus and minus, but if you put a number in front, if the number in front is bigger than 1, it's going to make a more narrow parabola than your base parabola. And if you have a fraction that's less than 1, then it's going to make it a wider parabola. So I wanted to address that here. So if I have y equals ax squared, then if a is greater than 1, it makes a thinner parabola. So it's very thin like this. But so I want to say a fraction that's less than 1, but it's got to be bigger than 0. So if a was something between 0 and 1, it's going to make a wider parabola. So it's going to look more like this. Whether it's up or down, right? It could be same thing for this one. You could have a very narrow, steep one that opens downward. Okay, so that's what the number in front does. I think actually I'm going to stop. I'm not going to worry about that last one. Let's move on. Okay, what else can we do with parabolas? Here's our base parabola, f of x equals x squared. I'm going to quickly draw that one. quickly as I can. Here's y equals x squared. Now let's think about the next graph, g of x equals x minus 3 squared. So y equals x minus 3 squared. Now, you've been seeing I've been using the same numbers, -2, -1. Here I might take a different approach here. And actually what I want to think about is, what would I plug into this so my y value comes out to be 0? It would be 3, right? Because 3 minus 3 would be 0. 0 squared is 0. So, and then if you pick numbers close to 3, if I plugged in 2, 2 minus 3 is -1, -1 squared is 1. If I pick 1, that's going to be -2 squared, which is 4. Let's go to the other side. This will be 1. 5 minus 3 is 2. 2 squared is 4. So plot these points, 3, 0, 4, 1, and 2, 1. 5, 4, and 1, 4. What you can hopefully see is this orange graph is the exact same graph as our base graph. The only thing that's happened is it's been shifted to the right 3 units. All of these y values, notice this point moved 3 units this way. This point moves 3 units that way. This point moved 3 units there, right? The vertex moved 3 units there. And that is true in general as well. When you put a number with the x and then square it, if it's -3, now we have to, this is a little bit confusing. That actually moves the graph right 3 units, right? 3 units. Whereas on this one, we'll sketch this one. Okay, we know how to deal with the negative. That just means it's going to open down. What's the color? Green. What this +2 is going to do is actually move the vertex left 2. If it's +2. The way to think about it is if you plugged in -2, -2 plus 2 is 0. So the vertex should be at -2, 0. Plug in -2, you're going to get 0. And then it's a negative parabola. So it is just going to open downward. It's going to look like this. So take away from this one. If I've got y equals x minus h squared, I'm going to put plus or minus. Let's do this. Let's do them two separate. Let's start over. If I've got y equals x minus h squared, the graph is going to move my graph, move my vertex. The vertex, the whole graph moves h units to the right. Whereas if I have y equals x plus h squared, which you can't see until I move that over, my vertex is going to move h units to the left. Okay. If we put this all together, what we can now, these are all the, pretty much all the things that you can do with a parabola. So let's come up with sort of a general formula for this. Any parabola could have all of these different, we call these transformations. You could have a number in front. It could be x minus h squared. It could be some number at the end there. This is sort of a general formula for a parabola. And what would happen is if it was x minus h, your vertex would be at h comma k, because your normal vertex is 0, 0. When I say that, when I say normal, what I mean is for your base graph f of x equals x squared, the vertex is always 0, 0. So if we have x minus h, that's going to move my graph to the right h units, and up k, that means the vertex is going to be at hk. And we already saw if this was plus h, then it's going to be at negative h. And if this was a minus k, then it would have to be at minus k. We're going to do some examples of this. The very quick introduction to graph transformation. Some of you know these transformation ideas, you know, the negative reflecting the graph over the x-axis. This doesn't just apply to parabolas. This applies to lots of functions, all of these transformations. Okay, so for example, right here, f of x equals x plus 1 squared minus 4. There is no number in front. Remember, the number in front was just affecting how wide and thin the parabola was. So this one's going to have sort of a neutral, whatever, wide or thin part to it. But this plus 1 is going to move my graph left 1. Why left? Because you would be plugging in negative 1 plus 1 would make that 0. That's how you always want to think about it. So I know my vertex is going to be at negative 1 because my default vertex at x is 0. Now, if x is negative 1, this part would be 0, and notice my y value would be minus 4, and that's because this is moving my graph down 4. So for the vertex, okay, there we go. Again, my default for my regular parabola is 0, 0. We've moved the vertex in the whole graph left 1, down 4, so that is my new vertex, negative 1, negative 4. I know it's a open facing parabola. It's going to open upwards because I can tell that this is, if I square this out, that's going to be a positive x squared. Now, before I draw it, it might be nice to have some other points so that I get an accurate graph. You can make a t-chart like we did before, but what is always nice when you're graphing, easy points to find are to find x and y intercepts. Just like we did with lines, if I want to find my y-intercept, I'm going to be setting x equal to 0, and that's usually easy to do. By the way, this is another reason we use this notation. So what I want to do is I want to plug 0 in for x and see what I get for y. With function notation, we write it like this. F of 0 means I want to plug 0 in for x, and whatever I get out of this is my y value. 0 plus 1 squared minus 4. That's 1 squared. 1 minus 4 gives me negative 3, which means my y-intercept is 0, negative 3. 0, negative 3 right there. Now my x-intercept, I always want to set y equal to 0. And since f of x is the same thing as y, I'm going to be setting 0 equals x plus 1 squared minus 4. Now, one way to solve it is to square this all out, subtract the 4, factor it. But another way we could do this is if I move the 4 over here to the left side, and using what we know about solving equations, if I take the square root of both sides, I have to remember to take plus or minus on the right side. So I get plus or minus 2 is equal to just x plus 1. If I subtract the 1, I'm going to put that right here. So I get negative 1 plus or minus 2 is equal to x. So there's two answers here. One value for x is negative 1 plus 2, which is 1. The other one is negative 1 minus 2, which is negative 3. So my x-intercepts are 1, 0, and negative 3, 0. 1, 0, negative 3 zeros right there. And then we can just connect these. There's our parabola. Let's try another one. Okay, take a second. See if you can figure out what the vertex is. And the vertex, this one has an A in front, a number in front. Remember, that just affects the width of the parabola. It doesn't really affect where the vertex is. You still want to think about what makes this part equal to 0. What makes this equal to 0 is x equals 2, right? Or I can think of this as my graph is moved right to, yeah, in fact, I'm going to write it like that, right to, and this means the graph is moved up 3. So my normal vertex, which is at 0, 0, is now at right 2, up 3. This vertex is at 2, 3. Don't worry about that number. All that does is affect how it opens. And as I was starting to say, the other trick to think about it is what makes this 0? What makes this 0 is when x is 2. And if x is 2, this whole term is 0, right? And then what would I be left with is just 3. So that becomes my vertex. Now it is a downward facing parabola. Downward facing, or opens down is the other way to say that. But let's get some more points. I know it's going to go this way, but let's find a y-intercept. And as we saw earlier, I can denote that by saying f of 0. That means I'm plugging in 0. -3, 0 minus 2 squared plus 3. -2 squared is +4. That's going to be -12. And that gives me not -9. So my y-intercept is 0, -9 here. Oh, what's up? And here. And as far as my x-intercepts, I'm going to set my function equal to 0. The best way to solve this, I think, is since this whole thing is negative, you can literally add all of that and move it over to the other side. I could then divide both sides by 3 to isolate the x minus 2 squared. If I divide this by 3, divide this by 3, that's just going to be 1. And then I can do the square root method that we did on the previous one. I'm going to take square root plus or minus on the right side. Gives me x of minus 2 is equal to plus or minus 1. If I add the 2 over, the trick is to put it in front of the plus or minus. It's going to be 2 plus or minus 1. 2 plus 1 is 3. 2 minus 1 is 1. As coordinates, this becomes 3, 0, and 1, 0. 3, 0, 1, 0. Remember the -3, we talked about the 3. If this number is bigger than 1, it actually makes it more thin. And you can really see this when I graph this. If I can plot these points together, it's going to be a really narrow parabola. Okay. All of the parabolas we've done have been in a certain form. Some books call it the graphing form because you can pretty much see the vertex of the parabola when it's written in a certain form. This one, notice, is a little different, right? So what I mean by that is when you see something written like this, a parabola, you can, with practice, quickly read off the vertex is x equals +2, y equals 3. It's right there. But that's because it's written in a certain form. This one's not written in the same form. And so how are we going to, it is still a parabola because it has an x squared, but it's not really easy to find the vertex. So what we're going to do is make it look like, what we want to try to do is make this parabola look like something squared plus or minus some number, because that's where we can read off the vertex. So to do that, we're going to do a process. I'm sure you've done this before. It's called completing the square. Completing the square. I'll write that down in a second. And here's the idea. We want to bump this -12 out of the way. And what we want to do is add something to x squared plus 4x so that not only does x squared plus 4x plus whatever number I'm going to add factor, it factors into 2 identical factors. I want this to be the same factor so that I could just write it as that factor squared. So there's a magic number that would make that happen. And there is a way to figure out what that number is if you can't really see it. What you do is you want to take half of this number, 4/2, divide it by 2, and then square it. 4/2 is really 2, so if I square that, that gives me 4, and that's the number that I'm going to add there. Now, by putting a 4 there, which wasn't there before, I'm totally changing the problem, and I'm not allowed to do that. So to avoid changing the problem, the minute I add 4, I'm going to immediately subtract 4 right next to it, because then 4 minus 4 is 0, and it's like I haven't done anything. But in fact, I really have. because here's what we could then do. X squared plus 4x plus 4, if I kind of put parentheses around that, what does that factor into? It factors into x plus 2 times x plus 2, which I could write as x plus 2 squared. And then the negative 4 and the negative 12, if I combine that together, makes this minus 16. Wish my writing was better. Okay, now with our practice, what we've done before, I can see that the vertex of this parabola, the vertex, what makes this 0 is negative 2. If x was negative 2, this whole thing would be 0, and what I end up with is minus 16. So my vertex is negative 2, negative 16. Okay, negative 2, negative 16. My scale only goes down to negative 10, so maybe we'll extend this here. 11, 12, 13, 14, 15, 16. Negative 2, negative 16 is like right here. Now let's find some other points here. I always start with y-intercepts because they're easy. You're just plugging in 0. And in this form, it's actually easy. If I plug in 0, that's going to be 0 squared plus 4 times 0 minus 12. And it's pretty easy to see that that's just minus 12. So my y-intercept is 0, negative 12. Okay, this was negative 10, negative 11, negative 12. So it's right there. This was negative 2, negative 16. And it's an upward facing parabola, so you can tell there's going to be some x-intercepts. We can find those. That's, you're always setting your function equal to 0. And actually, this factors x plus 6, x minus 2. If I set this one equal to 0, I'm going to get negative 6. If I set this one equal to 0, I'm going to get positive 2. So I have negative 6, 0, 2, 0. Negative 6, 0, 2, 0. Okay, let me put this on. Do my best to draw this parabola. There it is. Okay, so, oh yeah, and I said I was gonna, so this process right here, we refer to as completing the square. Completing the square. And it's a skill you should know how to do. I'm imagining on the placement test, there's going to be a question about completing the square. It is something that you use not only in parabolas, but in other situations too. It's a skill to know. Okay. So we're going to practice completing the square. For these, I think we've done enough graphing. A big thing to want to be able to find with a parabola is the vertex. And so to find the vertex of a parabola, we want to get it into that graphing form. So this one's kind of like the last one we did, and it's not in the right form, so we're going to complete the square. So once again, to complete the square, the trick is just bump out that last number, get it out of the way. And then you always take half of this number, you're going to divide it by 2, and then square it, and that's going to give me just 1 squared, which is 1. And so I'm going to add 1. But because I added 1 to make sure I'm not changing the problem, I'm going to immediately subtract 1. And then you separate these 3 right here. How does that factor? That factors into x plus 1 times x plus 1. These two together gives me negative 1 plus 8 is plus 7. And this becomes x plus 1 squared minus 7. So I can tell this is a parabola with a vertex. What makes this 0 is if x is negative 1. If x is negative 1, this whole term would be 0, and I'd be left with minus 7. And oh, and then the other thing, it says state whether it's the highest or lowest point. What they mean by that is because this was a positive x squared, even at the beginning, I know this is a upward facing parabola. So this vertex corresponds to the lowest point. Now, completing the square gets a little bit tricky when your coefficient of x squared is not just plain old 1. Because as I said, what we want to do is bump that 2 out of the way. But the other thing we want to do is we need to factor out this negative from the first two terms. So it's going to look like this. I'm going to bump that 2 out of the way. I'm forcing out the negative from the first two terms. So that's going to be x squared. And if you think about it, it's going to be minus 6x, right? Because I'm taking out the negative from positive 6. Or alternatively, if you distribute this back, you should see that I'm going to get these two terms. Other thing when you're completing the square to prevent making mistakes is you always are going to be adding something to this, and then you're going to be adjusting by compensating by putting something here, either adding or subtracting. We'll have to figure that out. Okay. Take half of this number, even if it's negative, square it. So that becomes -3 squared, which is +9. Now, here's the thing. This is why this gets tricky. It looks like I just added 9, changed my problem by adding 9, so it feels like I should be subtracting 9 to make sure I'm not changing the problem. But we have to account for this negative that we factored out. If I were to put that back in, what this really becomes is -9. So by putting that 9 there, it's effectively becoming a -9. So if I don't want to change the problem, I have to then add 9 here. I want this to balance out to be 0. That's a little bit tricky. Okay, so you have to think about what's in front. I'm going to give you another example of that in a second. Anyhow, if you then factor this, that is x minus 3 times x minus 3. 9 plus 2 gives me +11. This is -x minus 3 squared plus 11. And I can tell, okay, let's take care of the highest or lowest point. Because of the negative, I can tell that it's a downward facing parabola, and I can tell that the vertex is going to be, what makes this 0 is when x is 3. X is 3, the whole thing is 0, and I'm just going to be left with 11. So my vertex is 3, 11, and it is in this case, highest point. More here. Okay, complete the square here. Similar to the last one, I'm going to bump the 1 out. I'm going to take those first two terms, and I need this coefficient of x squared to be 1. So I'm forcing out a 2. So that's going to become x squared plus, if I force out a 2, that's going to become 5x. And I'm going to add something here, and then I'm going to compensate after I figure out what I'm adding. Half of this number squared is going to give me 25 fourths. Oh boy. All right. So then, kind of like the last one, I got to make sure I'm adjusting appropriately. I've changed the problem by what looks like to be 25 fourths, but again, I have to think about what this is really going to become. If I were to distribute that 2 back in, that's going to be 2 times 25 fourths is 50 fourths, which is 25 halves. So to make sure I'm not changing the problem, I'm going to immediately want to subtract 25 halves. Okay. And then I have what I need here. Now, here's a little tip here, because the next step is to factor this, but you kind of anticipating this is going to factor into a perfect square. It's going to factor to 2 identical factors. So if you think about it, the last two, it's got to be x, it's got to be plus, And the last number is going to have to multiply together to give you 25/4. So it's going to be 5/2, which not coincidentally, notice that the number here is exactly what we had here before we squared it. That's how it's going to factor. It's always going to play out that way. And then I've got to figure out what negative 25/2 plus 1 is, but we know how to do that using a common denominator. Negative 25/2 plus 1, 1 is 2/2, is going to be negative 23/2, minus 23/2. So my vertex, this is an upward facing parabola because there's a positive out front. So I know this is going to be my lowest point. What makes this 0? Negative 5/2. Once x is negative 5/2, I'm just going to be left with this, negative 23/2. That's my vertex, and this would be a lowest point. If you feel like you're getting a hang of this, maybe pause the video and try to complete the square for this parabola. Okay, so I'm going to do this now. We're going to factor out a negative 4 from the first two terms, bump the 5 out. That's going to leave me with x squared. I'm taking out negative 4 from negative 8. That's going to leave me with plus 2, plus some number, and then we'll compensate. Half of this, 2 over 2, is really just 1 squared. So this is just going to be 1. But here's the critical point. By putting that 1 there, what did I really change the equation by? I really changed the equation by negative 4 times 1, which is negative 4, right? Times 1 is negative 4. So to not make sure I'm not changing the problem this time, I need to add 4. Because this is really behaving like a negative 4, and I don't want to change the problem. This is going to become negative 4. X squared plus 2x plus 1 is x plus 1 squared. 4 plus 9 is plus 9. Downward facing parabola because of the negative. Vertex is negative 1, positive 9, which would be the highest point. Okay, told you this was a long video. Normally, I would spend 3 days on parabolas probably, and there is another way. Completing the square to find the vertex of a parabola, you're probably noticing, is not always an easy process. So it turns out that there is a shortcut for finding the vertex of a parabola when it's written in the form f of x equals ax squared plus bx plus c. And I'm going to just tell this to you, but I'm holding it to you to make sure in class tomorrow you make me show you why this works. I want you to know why. I don't want you to just think math is a bunch of formulas. There's a reason these things work, and it's usually something very logical. So here's how we do it. The x coordinate of the vertex, just the x coordinate, can be shown that, and I'm going to use the notation v sub x. It can be shown that it's always going to be negative b over 2a. I'm going to bubble that. Again, this is just the x coordinate. Remember, the vertex has two coordinates. One's the x coordinate, v sub x, and the other one I'm going to call v sub y. Once I know the x coordinate, how I would find the y coordinate of the vertex is I would just plug in v sub x into my parabola. So I'm just going to say f of v sub x. For example, we can test this out because let's do number 10 again. Number 10, we completed the square and saw that the vertex was negative 1, 9. So I'm going to use the same parabola. And here's how I could do this quickly. V sub x is negative b over 2a. So it's going to be negative of b is negative 8 over 2 times negative 4. That gives me positive 8 over negative 8. That gives me negative 1. This is exactly what I had for the x coordinate of my vertex. So then to find v sub y, I'm just going to plug that in to my parabola. Negative 4 times negative 1 squared minus 8 times -1 plus 5. This is going to be -4 plus 8 plus 5, and that gives me 9. So I put these together, I get -1, 9. We also found on number 8, there was number 8, we found the same parabola had a vertex of 311. So pause the video, see if you can use this new technique to confirm that the vertex was 311. B sub x is -b over 2a, -6 over 2 times -1 is -6 over -2, which gives me +3. And if you plug in 3, this is going to give you -9. This is going to give you 18. -9 plus 18 is +9. +9 plus 2 gives you 11. So pretty handy. -b over 2a is good. I still want you to know how to complete the square, though, because it is such an important thing to know. So you should have both of those techniques for finding the vertex. It's not bad to know 2 ways to find the vertex, is it? Okay, here we go. Another word problem here. Knowing how to find the vertex of a parabola is really, really useful because there are lots of applications, things that involve parabolas. And here's one, more of a medicine one. So suppose a patient takes a drug orally, and we want to think about, well, how does the concentration of the drug, how does it, what is it like over time? And if you kind of think about it, I know this is maybe not totally realistic, but if you think about the concentration over time, when time is 0, you just took this pill, what would seem to happen is the concentration is probably going to increase. And then as your body starts to process the drug, then the concentration is going to go down and eventually it'll be all out of your system, right? So you could view the concentration of the drug in your blood over time as like an upside down parabola. And hopefully you recognize this, even though we've got some funky decimals, because there's a negative t squared. This is an upside down parabola. So then when it says, what is the maximum concentration of the drug in the bloodstream and where does it occur? You can tell that's going to be at the vertex. This is going to be at the vertex. They're asking us to find the vertex. So now we're going to use the shortcut, the -b over 2a, but be careful because they put the t squared first term second. So I would probably switch that around and then make this plus 0.06t. So this would be your A, all of this, and this would be your B, and we don't have a C. It's okay. So okay, now think about your vertex here. We have different, usually we use X and Y. My vertex, the X coordinate is going to be a time, right? The time it takes for the drug to reach its maximum concentration, and the Y value is going to be the actual concentration of the drug at that time. So X is like T, Y is like C. So instead of writing V sub X like we did before, what I would say is V sub T is -b over 2a. So -0.06 divided by 2 times -0.0002 gives me -0.06 divided by, if you multiply that by 2, it's going to be -0.0004. So this is obviously going to be positive. Okay. Let's go down here. So this is going to be positive 0.06 over 0.0004. Okay. So, okay, working with decimals without a calculator. The smaller decimal is this one. So think about this. Like if I want to if I want to move a decimal place over 1, I multiply by 10. If I want to move it over 2, I multiply by 100. Remember that 0.06 is 6/100ths, right? So I'd have to multiply by 100. But if I want this to not be a decimal, I'm going to have to go multiply by 10, 100, 1,000, 10,000. So without a calculator, how you could do this is 0.0004. Is if I multiply top and bottom by 10,000, that's going to move my decimal place over 4 places. 1, 2, 3, 4. So at least the denominator will be 4. In the numerator, if I do that, I'm going to move it over 1, 2, and then I have to go 3, 4. So it's going to be 600. If I move it over 2 places, it'd be 6. Move it over 1 more, that'll, in other words, add a 0, that'll be 60, and then 1 more would be 600. And 600 divided by 4 is 150. What would my units be? Remember, this is time. This would be minutes, right? So in other words, it takes 150 minutes to reach maximum concentration. So that would answer the first part. Now, that's actually answering the second part. When does it occur? But what is the maximum concentration? I would then take this and put it back into my parabola. So my actual maximum concentration is the y-coordinate essentially of the vertex, which is really just plugging in 150 for t. So it'd be negative 0.0002 times 150 squared plus 0.06 times 150. Okay, here admittedly, that would probably need a calculator. So you reach for a calculator. I don't know what that is off the top of my head. And then just make sure you include the units, right? The concentration was measured in milligrams per liter. So this will be some number here. Okay, thanks for hanging in there. I know that's a lot. We'll practice more parabolas in class today and probably on Monday as well. All right, bye.